So far we have discussed the concept of torque and angular momentum for a single particle. Whenever a particle experiences a net torque, its angular momentum changes about same reference point. Let us now extend the concept of torque and angular momentum for a system comprised of two or more than two particles. Let us assume that in this system we have two particles, and these two particles, let them interact with the forces F1 and F2, small f1 and small f2. And from outside, let them experience the forces capital F1 and capital F2 respectively. This is point 1, this is point 2. This is the system of two particles. The torque experienced by a system of particles. This system has two particles, simplest system of multi-particle. The net torque due to the internal forces F1 and F2 is called internal torque. Let us talk about the internal torque. These two forces are internal forces because the particles, they attract or repel each other. In this case, let these 2 point masses or these 2 point particles attract each other. Therefore, these two forces must act along the same line. The line of action of both the forces are same. Let us take a reference point. O. With respect to this reference point, the point of application of this force F1 is R1. With respect to same reference point, the point of application of the internal force F2 is R2. The net torque due to the internal forces F1 and F2 about any point O is internal torque is equal to torque produced by this force F1 plus torque produced by this force F2. This is equal to R1 cross F1, and this is equal to R2 cross F2 according to the basic formula of the torque. Since these two forces are internal forces, since F1 and F2 are internal forces, they must act along the same line. They must be equal in magnitude, they must be oppositely directed, They must act oppositely and they must be collinear. They must be collinear. They must act along the same line. Putting F1 is equal to minus F2. In this expression, we have internal torque is equal to R1 cross F1 plus R2 cross minus F1. Put F2 is equal to minus F1. Then you can write R1 minus R2 cross F1 vector. Let this vector be x vector. By triangle of vector addition, we can write R1 vector plus x vector is equal to R2 vector. Or we can write this as the x vector, just reversing the direction. By triangle of vector addition, R2 plus x can be written as R1. R2 plus x is equal to R1. X is equal to R1 minus R2. So instead of R1 minus R2, we can write x cross F1. This is the x vector. This is the F1 vector. These two vectors are collinear. The angle between these two vectors is 180 degree. If it is collinear, it can also be 0 degree. But in this case, F1 vector and x vector, the angle is 180 degree. Since they are collinear, it may be 180 degree or it can be 0 degree. In both the cases, x cross F1 is equal to 0. So it gives us an idea that the internal torque is always equal to 0. The internal torque, the net torque, produced by the internal forces about any reference point is always 0. Tau internal is equal to 0. This is the concept. The net torque produced by the internal forces of a system of particles about any reference point is always 0. So internal torque is 0 for all the times. Let us talk about the torque produced by the external forces. Here we have proved that the torque produced by the internal forces as a whole will be equal to 0. Then the net torque is produced by the external forces. Hence, the net torque is equal to torque produced by the internal forces plus torque produced by the what? External forces. In this way, if you write the internal torque is equal to 0, we have the net torque experienced by the system about any reference point is equal to the net torque experienced by the system due to the external forces only about that reference point. The net torque experienced by a system of particle is equal to the net torque produced by the external forces only. This is the concept. This is the understanding. Whenever a system of particle experiences the internal forces and external forces, when you are calculating the net torque, don't include the internal forces because the internal forces as a whole will produce zero net torque. The net torque is produced by the external forces only. Let us take an example. You take two particles, they are interconnected by a spring. Let the spring be compressed so that it will experience a force F and minus F, equal and opposite. The compressed spring will push both the particles with equal and opposite forces. So if you take this as a system, its mass is m1, its mass is m2. This system and this system, the internal forces are the spring forces. If you take the spring force plus F, this spring force is minus F. If you take the spring force minus F, this will be plus F, because they are equal and opposite and collinear acting along the spring. The torque produced by plus F plus the torque produced by minus F, that is the internal torque, is always equal to 0 as per the previous concept. Then find the net torque experienced by the system of the particles interconnected by the spring and subjected to gravity. If you draw the free body diagram, in addition to the internal forces, we have the gravity forces. Gravity pulls both the particles down with forces m1g and m2g. G is the acceleration due to gravity. Let us take any point. To find the net torque, we have to choose the reference point. If we choose the reference point, the center of the spring and the spring is inclined at an angle of theta at this instant, and the length of the spring let be L. You take the center as a reference point O. This will be L by 2. This segment length will be L by 2. This is M2G. This is M1G. The net torque is equal to torque due to the gravity. Don't consider the internal forces. This gravitational force will apply a torque about this point in this sense. R cross M1G vector. This gravitational force applies a torque about this point in the opposite sense. R cross M2G vector. So, you can call it R1, you can call it R2. Torque due to this gravity force about this point is equal to R1 vector cross M1G. Torque due to this gravity force about this point is equal to R2 vector cross M2G. R1 M1G sin theta. Theta is the angle between these two vectors. Here the given theta and the theta in the formula may not be same for all times, for all examples. So let it be phi. R1 cross mg is equal to, if you take this as theta, phi is equal to pi by 2 plus theta. So R1 M1G sin phi. Direction R1 cross mg. R1 cross mg in anticlockwise sense plus KKF. Here it is R2 cross mg. You bring the two vectors to a point. Bring the tails of these two vectors to a point. This is M2G. This is R2 vector. Bring the tails. This is the tail of R2 vector. This is the tail of M2G vector. Bring the tails of these two vectors to a point. Then this angle is the angle between R vector and force vector. So R2 cross mg is equal to R2 M2G sin, let it be phi dash. Here phi dash is equal to, if this is phi, this is theta, phi dash will be equal to 90 minus theta. Evaluate sin phi, substitute. By substituting phi as pi by 2 plus theta, you can write sin pi by 2 plus theta in KAB direction. And here R cross mg, this will be, this is R vector, this is mg vector, R cross mg, this is in minus KAB direction, minus KAB direction. Minus R2 M2G sin pi by 2 minus theta KAB. So this is equal to R1 M1G sin pi by 2 plus theta is cos theta KAB minus R2 M2G sin pi by 2 minus theta is cos theta. So we are getting R1 cos theta and R2 cos theta. Or we can just write the magnitude of R1 is equal to magnitude of R2 is equal to L by 2. What is L? L is the length of the spring at this instant. It may not be the natural length. Length of the spring or length of the compressed. So M1J cos theta, or you can take J cos theta. R1 is equal to R2, that is L by 2. L by 2 J cos theta you take common into KKF M1 minus M2. And if M1 is greater than M2, the torque is positive. The torque is positive. Means the net gravitational torque, the net torque will point in positive z direction or outward direction And if these two masses are equal, this will vanish. We get no net torque. And if M1 is less than M2, this quantity becomes negative. So the net torque will be directed in negative z direction. The torque is negative means it will be inward. So under three different conditions, we can get three different answers. So find the net torque about the point O, the center of the spring. And this is the solution. Using the basics also we can solve the same problem, reducing some steps. Let me solve in that method. Using the second method, which uses the concept of torque is equal to the magnitude of the force into the perpendicular distance drawn from the reference point onto the line of action. P. In which sense this is R vector, this is F vector. R cross F, clockwise sense. R cross F can be given as P into F, the magnitude, and the direction by inspection you can understand by taking the direction in the using the formula R cross F. So if you use this concept, the torque about this point due to this force can be given as this is the perpendicular distance, that is this is L by 2, this is theta, this perpendicular distance P can be written as L by 2 cos theta. So M2J into L by 2 cos theta. In which sense? In clockwise sense, because this is R2, this is M2J. R2 cross M2J is clockwise, and here this is R1, this is M1G. R1 cross M1G. This is R1. This is M1G. R1 cross M1G will be in anticlockwise sense. So this force M1G produces anticlockwise torque. This force M2G produces clockwise torque. When you are adding this, you write net torque is equal to torque produced by the external forces only, because internal forces will never produce any torque as a whole. So the net torque about this point is equal to this force into this distance. This is P is equal to L by 2 cos theta. In which sense? In anticlockwise sense. L by 2 cos theta into M1G. Anticlockwise sense means outward or positive z direction. Torque produced by this force about this point is equal to this perpendicular distance into the magnitude of the force. The perpendicular distance is L by 2 cos theta and the magnitude of the force is M2G. Direction is given by R2 cross Mg clockwise minus KKF. So M1 minus M2 Lg by 2 cos theta KKF direction. Exactly same answer you are getting, reducing so many steps by using the concepts. However, both the procedures are self-sufficient. First of all, we should do the problem using the proper mathematical approach. Then by using the concept, we can solve the problem by reducing some steps. Under the same context, let us now find the torque acting on the system of particle taking two reference points. One is the center of mass of the system. Second is any reference point. The center of mass is C, any other reference point is O. You take this point P, on this point let a force act from outside or the external force. Fi is the force acting on ith point or point P. The torque produced by this force above the reference point O is torque of the force Fi about O is tau O is equal to R cross F, or you can just take the simple the force F instead of Fi. Then you can generalize the fact. The force F is producing a torque about this point, that's equal to R cross F. When you stand on the center of mass, you can see that this point is located in this direction at a distance of RPC. RPC is the position vector of this point P with respect to the center of mass. And this is the position of the center of mass with respect to this fixed, say it is fixed reference point. Using triangle law of vectors, we can write RC plus RPC is equal to R by using triangle law of vectors addition. So R can be written as RC plus RPC cross F. So you can write RC cross F plus RPC cross F after expanding the bracket or removing the bracket. We have two terms now. It is tau O. This torque is produced by the ith external force. If we add all the torques produced by all external forces acting on all points, then we have to take the summation. This is or we can just write instead of P, you can write I, this is ith point. Instead of P, you can write I. Ri cross Fi. Ri is equal to Rc plus Ric cross Fi. Rc cross Fi plus Ric cross Fi. And you have to sum all these torques produced by all external forces. When you are proceeding in general, we are getting these two terms. Here you can note that this vector is a constant vector for all the forces. Therefore, you have to take it out of the summation sign. RC cross F, you have to pull out of the summation, and we are getting the sum of all external forces plus Ric cross Fi, sum of this. This signifies the torque of Fi with respect to center of mass C, and the summation signifies that sum of the torque produced by all external forces with respect to center of mass. This signifies physically the torque the net torque produced by all external forces with respect to center of mass frame. I can call it tau C, and this factor is the net force acting on the system of particle. Let it be F net or net external force. Net force is nothing but net external force because the net internal force is how much? 0. Now the net torque about this fixed reference point is equal to the position vector of the center of mass cross the net external force plus the net torque experienced by all forces, the net torque given by all forces acting from outside taken with respect to the center of mass frame is tau C. This becomes another theorem which states that the net torque acting on the system of particles about any reference point O, suppose it is fixed point, is equal to the torque produced by all external forces with respect to center of mass frame plus the torque of the net force supposed to be acting at the center of mass. This is what is the torque produced by the net force supposed to be acting at the center of mass. On the center of mass with respect to the given point O plus the torque produced by the net force supposed to be acting on the center of mass with respect to the given point. So this is a theorem which states that the net torque acting on a system of particles about any fixed reference point is equal to the net torque acting with respect to center of mass frame plus the torque produced by the net force which is supposed to be acting at the center of mass taken or calculated or determined with respect to the fixed reference point. Using this idea or this particular theorem will form the basis of dynamics of a rigid body.